We tend to think of AI as uh, constantly leveling up, right? Like
Yeah.
it's always learning new tricks, unlocking, deeper understanding.
Yeah, that's the common picture.
But what if one of the main ways we're trying to teach these language models to reason isn't really doing what we think it is?
That's the really intriguing question at the heart of our discussion today. We're doing a deep dive into a brand new research paper just came out April 21st, 2025.
Okay.
And it's titled, Does Reinforcement Learning Really Incentivize Reasoning Capacity in LLMs Beyond the Base Model?
Right. Okay, let's unpack this a bit. Reinforcement learning with verifiable rewards, RLVR. It sounds technical, but it's actually a pretty big deal in training these large language models, isn't it?
Absolutely, especially for the complex stuff like math problems or generating code.
And the core idea is, well, fairly straightforward. You give the AI a reward when it does something right.
Exactly, and automatically verifiable rewards. So, did it get the right answer to the math question? Did the code it wrote actually pass the test?
Yeah.
And the goal is to encourage it through these rewards to develop stronger reasoning skills, basically saying, hey, good job, you reasoned correctly.
Okay, so that seems logical, but what's the catch? What's this paper questioning?
Well, the widely held belief, and what this paper really takes aim at, is that this RLVR process is the key. The key to allowing these LLMs to not just get better at things they could sort of already do, but to actually develop entirely new reasoning abilities.
Abilities that weren't there in the original, like the base model before all this extra training.
Precisely. We often hear about models like, OpenAI o1, DeepSeek R1, maybe Kimi 1.5. They're held up as these reasoning-focused models.
They rely heavily on RLVR.
That's the common understanding, yes, that RLVR is driving that reasoning leap.
So our mission today is to really scrutinize this whole idea. Is RLVR truly the, I don't know, the magic bullet for unlocking new levels of AI reasoning?
Or could something else be happening? Something less transformative, maybe.
The researchers behind this paper seem to think it's the latter. And if they're right, well, that could really shift how we think about training the next generation of AI, right? Are we maybe focusing too much effort on this one technique?
That's the critical question they're posing. Their whole investigation boils down to, does RLVR actually lead to fundamentally new reasoning capabilities in LLMs?
Okay, so how did they go about testing that?
It's quite insightful, actually. They started by looking at how we normally measure reasoning ability in these models.
Which usually involves just seeing if it gets the answer right, like on the first try.
Right, that's often a key metric, the
Yeah.
single pass success rate. But they also talk about the pass at K metric.
Pass at K, what does the K mean?
So K is the number of attempts. With pass at K, you consider a problem solved if the model gets it right in any one of its first K tries. So pass at 1 is the first try success rate. Pass at 10 means it got it right sometime within 10 attempts.
Ah, okay, so you give them more chances.
Exactly. And what's really interesting here is that this study pushes that K value way up. They use large values of K.
Why large values?
The idea is to really test the boundaries, to give both the original base models, the ones before RLVR training, and the RL-trained models, a whole lot of chances to solve a problem. See what they're truly capable of when you let them try and try again.
Okay, I'm starting to see where this is going.
Yeah.
So what did they find when they did that?
Well, this is the first really big, surprising finding. It's quite counterintuitive.
Lay it on us.
While the RL-trained models generally do better when you only give them a few tries, say, at small K values, like K1 or K4.
Which is what you'd expect, right? They've had the extra training.
Exactly. But as you increase K, as you give them more and more attempts, the base models, the ones without the RLVR training, start to catch up.
Catch up?
And in many cases, they actually achieve comparable or sometimes even higher pass at K scores than the RL-trained models, but only at these very large K values.
Whoa, okay, that is surprising. So the base model, the supposedly less capable one, can eventually solve the problems just as well, or better, if you just let it keep trying.
That's what the data suggests. It implies that the fundamental capacity, the potential to generate the correct reasoning path and answer might already be there in the base model.
It's just not as good at finding it quickly. Less efficient.
Precisely. The potential seems to be there, just hidden, perhaps. The RLVR training seems to make accessing that potential more efficient on the first few tries.
Okay, that leads nicely into the second surprising finding then. If RLVR isn't necessarily unlocking new reasoning, what is it doing? You mentioned efficiency.
Right. They looked into this using something called perplexity analysis.
Perplexity. Can you give us a quick sense of what that means in this context for listeners maybe not deep in the NLP weeds.
Sure. Think of perplexity as a measure of how surprised or uncertain the model is by the next word it's going to generate. Lower perplexity means it's more confident, its predictions are more focused, less scattered.
Got it. So lower perplexity, more confident predictions. What did the analysis show?
What's fascinating is that the analysis showed that the reasoning pathways, the sequences of words leading to a correct answer that the RL-trained models use, well, those pathways are actually already present within the possible outputs, the distribution of the base models.
So the base model could generate them?
It could, they're just less probable. RLVR training seems to basically bias the model's output distribution. It makes it much more likely to sample those known correct pathways.
Which explains why it performs better on the first few tries higher pass at 1.
Exactly. It boosts the efficiency of finding those solutions.
But there's always a but, isn't there? This boost in efficiency seems to come with a trade-off. The paper suggests this focus might actually limit the model in some way.
That's the second key part of this finding. By heavily biasing the model towards the paths that lead to rewards, RLVR might be reducing its ability or maybe its tendency to explore a wider range of possibilities.
So it narrows its scope. It becomes really good at the things it was trained on, but maybe less flexible or less likely to find solutions that are outside that reinforced zone.
That seems to be the implication. It's like digging a deeper channel for a river. The water flows faster and more efficiently down that channel, but it's less likely to explore new routes.
The paper has a figure 1, that illustrates this, right? It's showing efficiency going up, but maybe the overall potential, the scope at high K going down.
Yes, figure 1 is key. The left side shows that concept, visually more efficient sampling, but potentially a reduced overall scope. And the right side shows the metrics. Pass at 1 improves with RLVR training, as expected.
More efficient.
But pass at 256, so giving it 256 tries actually decreases as RLVR training progresses in their experiments.
Wow. So it gets better at the first guess, but worse when given many, many chances. That really drives home the trade-off.
It does. It suggests the RL-trained model becomes very good at hitting a known target efficiently, but less capable of searching broadly for potentially unknown or less probable targets.
Okay, so finding #1. Base models can catch up or surpass with enough tries. Finding #2. RLVR boosts efficiency, but might reduce the overall scope. Was the third surprise.
The third finding looks at the specific reinforcement learning algorithms used. There isn't just one way to do RL. There are different algorithms like PPO, GRPO, Reinforce++, and others.
Do they work differently?
They have slightly different mechanisms for calculating updates and guiding the learning. PPO, for instance, is known for being relatively stable. The researchers wondered if maybe the type of RL algorithm made a big difference here.
And did it?
Surprisingly, not really. They found only slight variations in performance between these different algorithms.
Okay.
And crucially, what they call the sampling efficiency gap. Remember, that's the difference between the RL model's performance at low K and the base model's performance at high K. That gap remained pretty large across all the different RL methods they tested.
So it's not just about picking a slightly better RL algorithm. The fundamental limitation seems consistent.
That's what it looks like. They used a framework called VRL to make sure they were comparing these algorithms fairly, too. You can dig into the specifics in Figure 7 and Tables 2 and 3 in the paper if you're curious about the algorithm details.
Okay, interesting. So similar results across different RL flavors. What's the fourth main finding? This one contrasts RLVR with something else.
Yes, distillation. This is a really important comparison they make.
Distillation. That's where you train a smaller model to mimic a bigger, more powerful one, right?
Yeah.
Like a student learning from a teacher.
Exactly. And the paper points out that unlike RLVR, distillation can actually seem to introduce genuinely new knowledge or capabilities. It can expand the scope of reasoning beyond what the initial base model could do.
So learning from a better model's outputs can actually teach the student model new tricks in a way that just rewarding the student model for its own correct answers doesn't.
That appears to be the case based on their analysis. There's a great comparison in Figure 6, right side, in the paper, showing how base models, instruction-tuned models, RL-trained models, and distilled models stack up. The distilled one shows a clearer jump in capability.
Do they have an example of a distilled model showing this?
Yes, they mention the DeepSeek R1 Distill Quen 7b model specifically as one that demonstrates this kind of expansion of reasoning ability, seemingly beyond the base Quen 7b model it was distilled into.
So distillation seems fundamentally different from RLVR in its effect on reasoning scope. That's a critical distinction.
It really is. It suggests that the source of the learning signal matters a lot. Is it just reinforcing existing discoverable paths like RLVR, or is it absorbing new patterns from a more capable source like distillation?
And they didn't just test this on one kind of problem, did they? They looked across different areas.
No, they were quite thorough. They checked if these findings held up across mathematics, code generation, even visual reasoning.
Okay, so for math.
They used standard benchmarks like GSM-8K, Math 500, and also a challenging one called AME24. You can see the results in figures 2 and 3. The same trends appeared. RL helps at low K, base catches up at high K.
And code generation, similar story.
Yep. Using benchmarks like Live Code Bench, Human Evil plus 2 MBPP plus Day. Again, figures 4 and 5, left side, show that same pattern. RLVR gives that initial efficiency boost, but the base models show surprising potential with enough samples.
What about visual reasoning? That seems quite different.
They tested on tasks like Math Vista and Math Vision, which involve understanding images to solve math problems. And figure 5, right side, shows, yet again, consistent results. The pattern holds across these diverse domains.
That's pretty compelling. Did they account for things like the model just getting lucky, especially on math problems when it tries hundreds of times? Maybe getting the right number, but with nonsense reasoning?
They did consider that. They specifically mentioned trying to handle hacking, where a model might find a shortcut to the answer without proper reasoning. They performed some manual analysis of the chain of thought, the reasoning steps generated by the models.
Oh, interesting. What did that show?
They provide examples in the appendix, figures 18 and 19. It seems even the base models, when they eventually found the right answer after many tries, often produced coherent reasoning steps, suggesting it wasn't just random luck in many cases.
Okay, that has weight.
And for the AME24 math benchmark, they knew some questions might be easier to guess, so they filtered those out and reran the analysis on the harder subset.
Right.
Same trends. Figure 9 shows the results on the filtered set. The conclusions still held. The consistency across tasks and after these checks really strengthens their core argument.
It definitely seems like a robust finding then. So why might this be happening? Why does RLVR seem limited to mainly improving efficiency rather than expanding fundamental reasoning? The paper offers some ideas.
It does. They touch on a couple of key possibilities. One is just the sheer scale of the problem for the RL algorithm.
How so?
Think about the action space, all the possible things the model can do at each step. For a language model, the action at each step is choosing the next word or token. The vocabulary is huge.
Tens of thousands, even hundreds of thousands of options.
Exactly. Compared to, say, a game like Go or chess, where the number of possible moves is large but finite and structured, the language space is astronomically vast and less structured. It's incredibly hard for an RL algorithm to effectively explore that space and stumble upon truly novel sequences of reasoning purely through trial and error and reward.
Now that makes sense. It's just too big a space to search effectively from scratch. And what's the second point? Something about the starting point.
Right, the pre-trained priors. RLVR isn't applied to a blank slate AI. It starts with a base model that has already gone through massive pre-training on text and code.
So it already knows a lot. It has ingrained patterns and tendencies.
It has very strong priors about what sequences of words are likely, what constitutes sensible language, and probably what plausible-looking reasoning steps look like based on everything it read during pre-training.
And RLVR works with those priors.
Yes. While those priors are essential for making the model generate anything useful at all, they also constrain the search. Policy gradient algorithms, which are common in RL, tend to reinforce actions that are already somewhat likely if they lead to a reward.
So if a correct reasoning path is already sort of plausible according to the base model's priors, RLVR is good at making it more plausible, more likely to be sampled.
Exactly, boosting efficiency.
But if a completely new way of reasoning is very unlikely according to those priors, RLVR might struggle to ever discover and reinforce it, even if it would lead to a reward. It's just too far off the beaten path.
That seems to be the hypothesis. The initial priors are so strong they might overshadoww the reward signal when it comes to genuinely novel exploration.
The paper mentions something about using distillation first, then RL.
Yeah, they briefly suggest that maybe applying RL after distillation could be a way forward. The distilled model might have a better, more informed prior, potentially making RL more effective at refining those improved abilities. But RL on its own, applied to the base model, seems limited.
Interesting. They also looked at temperature settings. Quickly.
Just briefly. Temperature affects the randomness of the output. higher temperature, more randomness, potentially more exploration, but also more nonsense.
What was the takeaway there?
They noted, and you can see this in Figure 10, that the base model's performance tends to drop off more significantly at higher temperatures, probably because it starts generating less coherent stuff.
Whereas the RL model,
The RL trained model seemed more stable across different temperatures, likely because it's been so heavily biased toward specific rewarded pathways, it's less prone to going completely off the rails, even with more randomness.
okay, so let's try and wrap this up. After this deep dive into the paper, what's the main headline, the big takeaway?
I think the core message is that RLVR, this popular technique, seems to be primarily making large language models more efficient at using reasoning abilities that were likely already latent within the base model.
So it's sharpening existing tools rather than forging entirely new ones.
That's a good way to put it. And the really surprising part is that revelation about the base models that given enough attempts, enough sampling, they can often match or even beat the RL-tuned models on these complex reasoning tasks.
It suggests the raw potential might be broader than we assumed, just harder to access reliably.
Exactly. The underlying capacity might have been there all along, hidden beneath the surface of probable outputs.
This really does make you pause and think, doesn't it? What are the implications here for the future? If we want AI that can truly reason in more advanced, maybe even novel ways.
Does this mean RLVR, at least as currently applied, isn't the whole answer? Does this suggest we need to perhaps rethink our training strategies, maybe focus more on things like distillation, or find new ways to encourage genuine exploration beyond the pre-trained priors?
These are definitely fundamental questions this research brings up. It really challenges some common assumptions in the field.
It certainly pushes us to think beyond just optimizing for efficiency on known solution paths and consider how we can actually broaden the scope of AI reasoning.
Well, this has been fascinating. If you, the listener, want to get into the nitty-gritty, we absolutely recommend checking out the original paper. Again, it's Does Reinforcement Learning Really Incentivize Reasoning Capacity in LLMs Beyond the Base Model?
And they also have a project page online with more details, visuals, and data. You can find it at limit-rlvr.github.io. That's limit-of-rlvr.github.io.
Definitely worth exploring if this sparked your interest.
Ultimately, I think this research is a valuable step. It highlights that the quest to truly unlock and, importantly, expand the reasoning potential of AI is far from over. These findings give us important clues for how we might navigate that path more effectively going forward.